Hello, I'm David. I'm the coordinator of the Maths Learning Centre at the Uni of Adelaide. It's semester 1, 2022, and this is the revision seminar for Maths 1B. And we have several people who have put many requests, and I will do my best to talk about as many of them as we can. Okay. All right. The first thing I'd like to talk about is the two variable function stuff. I don't know any one person asked about that, but it is something that I reckon I can do in a little, like half an hour, and then we can get onto the probably series for a bit. Okay. Okay. All right. Well, there's two big ideas that are going on here. So let me step back a moment and just get into the groove. When you've got ordinary functions and you have a function like f of x, then what f of x does is every input for x produces an output, which is a number. And so you've got number, input, and you do the function f, and you get an output. And that's what a function does. Cool. And you can imagine having all the inputs that you could possibly give, and each one of them produces an output. So, for example, I could have the function that when you put 0 in, it produces 5, and when I put 1 in, it produces 7, and when I put 2 in, it produces 9, and when I put 3 in, it produces 11, and when I put 4 in, it produces 13, and so on. That would be a perfectly good function. Cool. So it's just an example. And that's fine. That's lovely. And you could, you normally represent them as a formula, like this is the function f of x is 5 plus 2x. Starts at 5, and every time you go up 1, you add 2, which is what this says here. Okay. And that's great. And you can, if you want to, represent these answers by doing a height at every position. And so I could go, all right, well, I've got a 5 at this spot, and I've got a 7 at this spot. That's not a 7. A 7 at this spot, and a 9 at this spot, and an 11 at this spot, and so on, right? And when you lay all that down, you get this wonderful little graph. You go, oh, look, it's a straight line. Okay, so that's one way of imagining what a function is doing. We interpret all of the numbers here as heights, and then you can create a graph from that. All right, so that's functions. That's one idea. The other idea separately is that, ignore the functions for a moment. The other idea separately is that I can draw a graph by saying, for example, that, so I can create an x and y coordinates and label every point by what it lines up with the x and y axes. We're used to doing that. This is the point 1, 2, for example, because it lines up with 1 on the x-axis and 2 on the y-axis. And I can drawing on this picture in a different way. I could create a drawing by saying, that, for example, 2y minus 4x equals 10. And I could decide whether a point needs to be colored in as part of my drawing, depending on whether it satisfies this equation or not. And so I could say, well, 2 times 1 minus 4 times 2 is minus 2, so it's not 10, so this point's out. Whereas the point 5, 0, so 2 times 1 minus 4 times 2 is minus 2, which is not 10, and so that's out. But 2 times 5 minus 4 times 0 is indeed 10, and so that point's in. And so I could get every point and I could sub it into this formula and see if it came out to 10 or not. And all the ones that come out to 10, I can collect them all together and I get this line here. So these are the points where this calculation comes out to 10. And every other point the calculation does not come out to 10. Okay, so that's a separate idea. And this idea up here is connected to that idea by going, well, just a second, I've got x coordinates. And if I interpret those numbers here as heights, then I can go, well, this one's 5, and this one's 7, and this one's 9, this one's 11, and when I'm halfway, it's there, and when I'm halfway, it's there, and I can calculate the same picture. So I have two different ways to produce the same picture. This one is saying that there is a function which says 5 plus 2x, and I'm going to say that the value of y is the same as what the function produces. And this one is random formula. Okay. And people have been studying coordinate geometry for such a long time that we don't bat an eyelid. Well, maybe we do, but mathematicians don't bat an eyelid at seeing an equation like this and an equation like this representing the same thing. Okay, cool. Nothing up my sleeves. This is a calculation that I do based on both the x and y coordinate of a point. In that sense, this bit is a function of both x and y simultaneously. This thing was a calculation based on only the x coordinate, and every x produced a number. Well, this is a calculation based on both the x and y, and every combination of x and y, every point produces a number. At this point, the number was -2, and at this point, the number was 10. And here at 1, 2, 3, 4, 5, 6, 3, the number came out to 2 times 6, minus 4 times 3, which is 0, right? Yep, which is 0. And this number, it produces its own thing, and this point, it produces its own thing. Every point has its own number. The only ones I care about are the ones where they all come out to 10, but there are other numbers. But if I treated this as a function of its own, then there would be a number at every point in the plane in the same way as there was a number at every point on this line. And I could interpret all of those numbers as heights. And those heights would produce a big thing here, right? So this one produces the answer 0. This one produces the answer -2, which will be below the page. This one produces the answer 10. And so on. Different points would produce different answers. And so they'd all be different heights. And those heights together would produce a surface. So that's one way to make a surface. So one way to make a surface is an x and a y lying down. I'm imagining my x and y plane and then tipping it over like this. And then at every point, there is a function value that I can draw a height or a depth for, and those things all combine together to produce a surface. And that surface is the graph of this function. How are we feeling? Okay. But wait, nothing up my sleeves. I can do the same thing, right? In this one, I had a line and I interpret all those as heights, and that produced a graph that way. But I could also create a formula at every point and select out just the ones that come out to a particular answer, and that produce a graph that way. And now I've got a formula at every point and I interpret them all as heights, and that produces a 3D graph. The other way to produce a 3D graph is the same thing as I did in 2D, which is to just start out with an X and a Y and a Z and just write down a formula. You know, write down a formula like something like that, for example. And I could color in all the points with 3 coordinates that when I sub those 3 coordinates into here, it produced the answer 3. And some of these points in space will produce the answer 3, some of them will produce a different answer. And when I collect together all of the ones that produce the same answer, it will produce a surface. And we could keep doing that if we wanted. So that's the point of this, is that in 2D, there are 2 ways to make a graph. You can either have a function that produces, and all of the y coordinates are the answers that when you sub in X, or you can have a 2-variable function and choose the ones that have a particular answer. And to make a graph in 3D, you can either have a function that takes X, Y and produces an answer, and the Z coordinate, you know, this surface is not Y, this, oh, that's the Y axis there. This surface is the Z is equal to the function of X and Y. Have a 2-variable function and all the Z represents all the heights. And so you take the X and Y coordinates and it spits out the correct Z coordinate. Or you can have a formula that says some sort of formula involving X, Y, and Z, and you choose the ones that have a particular answer, and that produces a function as well. And they're both ways of making functions, of making surfaces. There are 2 ways to make a curve, 2 ways to make a surface. I'm just going to see if I can summarize that in a useful way on the piece of paper so that someone reading it can have this. Two ways to make a curve is, one way is to have a function f of x and then the y coordinate each point is f of x for the matching x coordinate. So you run along the x-axis and then the y coordinate of each point is f of x. And so you write y equals f of x. That's that. The other way to make a curve is to have a function f of x, y, and calculate f of x, y at every point and pick out the ones with a specific answer. And that will be f of x, y equals some number. And they are 2 different ways to produce a curve. And ways to make a surface, it's z equals f of x, y, or f of x, y, z equals constant. I'm just going to write that all down again. run around all the points in the plane. Then the z coordinate of each point is f of xy. And so you'll have z equals f of xy. The other way to make a surface is to have a function f of x, y, and z. So normally they'd call it g, but it don't matter. It's just a function. This is a different function to that one. And calculate f of x, y, z at every point in space and pick out points with a particular answer. And so you'll get something more like f of x, y, z equals constant. All right, how are you feeling about that? Okay. Cool. That is making surfaces in 3D and making curves in 2D. They are similar sorts of approaches and they link up with each other. So a curve in 2D is the place where a 2D function is equal to a specific value. But you can make the graph of the entire 2D function and that would make a surface in 3D. Yeah. How's everyone feeling? Okay. Cool. Right. And so what this means is if I'm interested in curves, then to have a full and complete understanding of curves, I need to understand both functions of one variable and functions of two variables. And to have a full and complete understanding of surfaces, I need to understand functions in two variables and functions in three variables. Right. Okay. So stop there for a second. All right. I've never made that point so explicitly before, so I'm very happy with myself. Okay. So not all surfaces can be made in the function way, like in the... Not all surfaces can be made this way. But is the grand hope of mathematics that all surfaces can be made in this way. So only surfaces that satisfy the vertical line test, same as a vertical line test back in when you were doing inverse functions, can be made this way. So something like a sphere, which has a top and a bottom, can't be made this way, but it can be made this way. So, yeah. Okay. So, those two perspectives create different ways of producing, especially importantly, a tangent plane. So that's what I'm going to talk about. I'm not going to talk about all the other stuff, just the tangent planes and the extrema. Okay. Maybe just extrema. Just give me a sec. Just going to draw a picture. This is a surface. That's not going to work, is it? All right. This is a surface. You guys can see it from where you are, but I'm hoping that the people in the Zoom can see it too. I could make this surface either as imagining that down here on the floor there's an x and y axes, and each point produces a function value, and then I go up that height and it produces the correct spot on the surface. That's the classic way of making a surface. But I could also have, oh, I've just recognized you. Sorry. Hello. Took me this whole time. The other way is to have some sort of thing where every point in space has a number that goes with it, and I pick out just the ones that come out to say 7 or something, and it produces this thing. If I picked out the ones that maybe make it equal to 10, it might have been up here. The ones that make it equal to 6 might have been down here, something like that. Okay, so I can see the surface. If I'm thinking of it as a function of the x and y axes, x and y points producing heights, then I can see that the value of that function is highest here. That's the highest point on the surface. And the lowest point on the surface is down here at the bottom of this valley. This valley is not quite so deep. If you just turn it this way, you can see that. This valley is deeper than this one. The lowest point, the lowest value that the function produces is at the bottom of this valley. And the highest one that the function produces is the top of this hill. But this one is higher than all the points around it. That's a local maximum. And this one is lower than all the points around it. That's a local minimum. And this one is the lowest if you're going this way, and it's the highest if you're going this way. That's a saddle point. Right. So that's surfaces, and they're the different features of a surface. They have maximums and minimums. There can be local maximums. These are both local minimums. But this one's the global minimum. It's the lowest point of all. They're both lower than the points around. And so they call them extrema, or one extremum, two extrema. So all 4 of these are extrema, local extrema. This is a global extremum, and this is a global extremum. They are extreme points. They're right at the edge of all the things that it can produce. This is not an extremum in any sense. It's below some points, it's above other points. But what they are places where the tangent plane is flat. So I need to draw a tangent plane. Ah! Need a pencil as well. So if I'm here and I travel in that direction, I'll come across this curve like this. And at this point, when I'm going in that direction, I'll be going upwards. And at this point, when I'm going that direction, I'll be going downwards. And in the middle, I'll be going momentarily flat. And if I went across the same point just here, but in this direction, then on this side I'll be going down, on this side I'll be going down as well. And so different directions going through that point will be different slopes. It's steepest going that way, but if I was going this way, it's not quite so steep. So those things are called tangents. And if at this point I look at all of the directions that this points, those together will form a plane. And that plane is tangent plane. So if I sit it just neatly on the top of the thing, it just touches it at one point. It is possible for the tangent plane to slice it in another spot. It hits it again over there, but that's what a tangent plane is. So at this hilltop, the tangent plane, very lucky you can see it, is perfectly flat, like perfectly horizontal. And so those extrema, the tangent plane is perfectly horizontal, which means that no matter which direction you face, you are technically neither going up nor down at that moment as you come across the top of the hill. And so to find an extremum, you need a place where no matter which direction you face, the slope in that direction is 0. So those arrows I was making with my line pencil are called directional derivatives. Not the arrow itself is a tangent, but the speed at which it goes up or down is the directional derivative. So the directional derivative is a number. The pencil is a line, but the directional derivative is a number that is the slope of that line. How quickly it goes up for every one across. Okay. So what I need is the slope to be 0 in every direction at a particular point. Some points, the slope is 0 in one direction, but no other direction. We saw one of those on the side of our thing. And some points, the slope is 0 in every direction. Oh, damn it. It's not too bad. There we go. At the saddle point, the slope is still 0 in every direction. It's just that it's neither the top nor the bottom. It happens sometimes. So we need an idea of what slope is. And we have partial derivatives, which tell you the slope in a particular direction in the parallel to the x-axis. If when I look down at where I'm moving along the x-y axis, the slope in that direction is the partial derivative in the x, and there's partial derivative in the y, and then there's directional derivatives. These are things. I'm just going to write them all down. So we're imagining this as the graph of a function at the moment, and then we can say that dz on dx is the speed that z changes as x moves forwards. That's what it is. And the way you do it is you differentiate this function pretending that y is constant. And dz on dy is the speed that z changes as y moves, which is differentiate pretending that x is constant. And those both things are examples of directional derivatives. Because what you're doing when you, as x moves forwards, is to say that you're going in the same direction as the vector 1, 0. And this is the direction of 0, 1. And so these are examples of directional derivatives. And a directional derivative is the speed that z changes as x and y move in the direction of a particular vector. Okay, so just wait. So the directional derivative in the direction of u of the function x, f at the point x, y, is the speed that z changes as x moves in the direction of the vector u. And I drew those with my rotating pencil as a directional derivative. The slope of that line was a directional derivative in all these different directions. And these are already directional derivatives. This is the directional derivative in the direction of 1, 0, and this is the directional derivative in the direction of 0, 1. But what you need to do in order to calculate this, and it's very, very clever, is that if I stood on that surface as a very small creature, like an amoeba, like a single-celled animal that's very small, it would feel flat. Not horizontal flat, but just flat like a plane. And in a plane, if you move a little bit one way and a little bit another, if you move in a particular direction, it's the same as moving on a plane. If you move, oh, sorry. Let me just check my, am I back yet with the mic? Okay. I must have knocked it with my paper. If you move a little bit, if you want to move this direction, you can go this way and this way separately and it'll work out the same. It won't work necessarily on a curved surface, but it works very well on a flat surface like a plane. And if you're very close to this surface, it will feel flat. And so that's what we're doing. That's what derivatives are all about. And so what will happen is you're going to get like dz on dx. Just a second. I'm just going to shortcut it. You're going to get how quickly the amount that z moves when you move in this direction is going to be how quickly z moves when you move in the x direction times how far you go in the x. And this is going to be dz on dy times how far you go in the y. That's the story. And then this is a dot product. And this vector is how far you've moved, which is what u is. And so it turns out that what you get is this thing dot with the vector u. Don't know if this explanation helps, but I like it. And this thing here is called the gradient of f. Yeah. So I get gradient of f dot u. So that's how you find directional derivative. Like the shortcut is you don't have to do any of this stuff. It is the speed that z changes if you move in the direction of u. What you need to do is figure out both the partial derivatives, dot it with the direction you're going, and that'll work. It'll only work if this is a unit vector. You can still say, as I move in the direction of the point 1,7, you're still allowed to say that sentence, but when you do the calculation, you have to use a unit vector that's in that direction. Okay, well, here's the thing. At those extreme points, if you want all of the directional derivatives to be 0 in every direction, you're going to need this vector to be 0. So that when you dot it with this, you always get the answer 0. And so at an extreme point, the gradient of f is going to be the 0 vector. Which means that both the partial derivatives have to be 0. And that is how to find extreme points of a function. You have to figure out what the partial derivatives are. You have to make them both 0 and find all the x's and y's that make them both 0 simultaneously. But what we actually call it, this happens at an extreme point, but if that happens, it doesn't have to be an extreme point. Because the saddle points, that happens as well, but they're not extreme. And so we actually call them critical points. I'm probably going to do a really bad job of this, just making one up, but I'm going to do this. Find the critical points of this function. So, to be a critical point, you need both the partial derivatives to be 0. So first I need to calculate there's actually another notation for this. You don't have to call it dz on dx. You could call it, if you want, f little x, if you want like that. They're the options that you get to choose. If you want to do dz on dx, you have to say let z equals, if you want. Technically, you're allowed to say df on dx, if you want. So f sub x of x and y that means that the x counts as a variable and the y counts and everything else counts as a constant. So derivative of x squared is 2x. The 2 and the y are both multiplied on, so they'll still be multiplied on afterwards. And the derivative of 2x squared is 2x. The y doesn't have any x's in it, so it counts as a constant. And when you differentiate constants, they disappear. And I'll do the other derivative as well. That doesn't have any y's in it, and so it will disappear when I do a derivative with respect to y. All right, this is the constant that's next to the y. If it had been 7y, the derivative would have been 7. If it had been 15y, the derivative would have been 15. Because it's 2x squared y, the derivative is 2x squared. And then this derivative is 3y squared. Cool. Cool. And so to be a critical point, they're both 0 at the same point, at the same time. They both have to be 0 simultaneously. Whoop, that's a 2xy, sorry. There are many ways to deal with this, and you just have to figure it out when you get there. Usually one of them is easier to solve than the other. Sometimes you can solve one to figure out specific answers for x and y and then sub those into the other one. Sometimes you can solve one to figure out y in terms of x and then sub that into the other one and it tells you what the x's are. At the moment, I can see that I can factorize this one like that. And so I get that either x is 0 or y is -1 based on this information here. Because multiplying things together to make 0, one of them has to be 0, so 2 can't be 0 because it's 2. X could be 0 or 1 plus y could be 0, which makes y -1. I'm just going to give them number 1 and number 2. Sub into number 2. So if x is equal to 0, I get 2 0 squared minus 3y squared is 0. So I get minus 3y squared is 0. That's only going to happen if y is 0. Because I'll divide by the -3 and then square root and I'll just have 0. Or y equals -1 will produce 2x squared minus 3 times -1 squared is 0. And so I'll get 2x squared minus 3 is 0. So 2x is 3. And so x is 3 on 2. And so I get 2 critical points. X is 0, y is 0, that's this one here. And x is 3 on 2, y is -1. But sometimes it's more complicated than that. Sometimes, oh, that's an x squared. Damn it, David, what are you doing? All right, sorry about that. So the x is actually plus or minus the square root of 3 on 2. And so I get 3 critical points, actually. So this one, when I put x equals 0, the only choice for y was 0. When I put y equals -1, one of the choices was √3, and the other one was -√3 on 2. But they both went with y as -1. Glad I noticed that. Okay, so they're the critical points. That's the end of finding critical points. But there is a thing that we haven't done, is we haven't figured out whether they're local maximums or local minimums or saddle points or whatever. And that's the bit you really wanted to know. just realized that I should have had my microphone on this entire time. How's that? Is that any different at all? What about that? Oh. Okay. Okay. Well, that's extreme. That's marginally better. Okay, good. All right. So the next stage is, well, how do you decide which one is which? To do that, you need to do an extra calculation. To decide if it's max, min, or saddle, we have to do this. So calculate the second derivatives. Technically, you can do f of yx, but these two will always be the same. If it's possible to calculate them, they will be the same. And then you calculate this. Oh, sorry. Oh yeah, cool. That's I get it. Now I think they call it delta, the discriminant, which is the determinant of this matrix. And then you have to do this separately for every critical point. Sub in the x's and y's and figure out what this works out to be. And then there's two layers of choice. If the discriminant is negative, then it's a saddle point. If the discriminant is 0, then nobody has any idea it could be anything. And if the discriminant is positive, then that means it's either a maximum or a minimum. But you don't know which one. And so then what you have to do is look back to this point and see whether these numbers were positive or negative. If fxx or fyy, it doesn't matter which one. If this is positive, then what that means is it's a minimum. Because fxx is the second derivative in the x direction. And when second derivatives are positive, it's concave up, and therefore it's a minimum. And if fxx is negative, then it will be a maximum. And we don't have to consider what happens if fxx is 0, because if fxx is 0, then you're guaranteed to get one of these two options. So that actually can't happen in the positive case. So that's good. So that's the two-stage solution. You have to first figure out what the delta is, and then if it's negative, it's a saddle point, you can just stop. And if it's positive, you get a maximum or a minimum. And then the next stage is that you have to then look at the things that went into calculating it and do that. So my example is, I'll continue, find so normally they'll say classify the critical points. And I'll do the same function I did last time. So we have to find the critical points. And you do all this working and you end up with 0, 0, root 3 on 2 minus 1 and minus root 3 on 2 minus 1. They are the critical points. And then we'll also have to find the second derivatives. So we had that f sub x was (2x plus 2xy), and f sub y was 2x squared minus 3y squared. And so fxx will be the derivative of this with respect to x again. So derivative of 2x is 2. The derivative of 2xy, well, the 2y is the constant that's multiplied by the x, so that will be 2y. And if I differentiate this with respect to y, I will get, that doesn't have a y in it, so that'll go away. The number attached to the y is 2x. And just to be sure I'm doing this right, so this is d on dx this way, and this is d on dy this way. I could do d on dx, and it should produce the same answer, which it does not, so I've done something wrong. Don't tell me I did something wrong like pages ago. Yep. Way back. Oh, that would be a 4x squared, wouldn't it? So here we are back here. We've got a 4x squared just here, isn't it? Just there? Yeah, yeah. Because there was already a 2, wasn't there? 2 times 2 is 4, isn't it? Not 2 times 2 is 2. Good-o. And so this would be a 4 here. And so when I pull the 2 out x, I'm going to be left with a 2y. Oh, man. And so the y would now be minus a half, wouldn't it? Great, 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 great. Sweet. That's okay. We can fix it. And so where's the rest of my working? So the x equals 0 is still fine, that bit works. And the y is minus a half. That'll make it 3/4, 3/8. Okay. Cool. And this is why we do these checks, to make sure we get them things right. So it's actually 3/8 here. And this was a 4 here, yep. And so that's now a 4y there. And when I differentiate this, I'll get a 4x. And differentiating this with respect to x does indeed produce 4x. Okay. So there you go. Handy way to make sure you get it right is that they should work out to be the same. And then if I differentiate this with respect to y, I'll get f of y is minus 6y. Okay. And so my discriminant times these two together. So minus 6y times 2 plus 4y, and I'll minus this squared. So that's what the discriminant works out to be. Looks very much like it's mostly going to be negative, but we'll see how we go. So at 0, 0, the discriminant is minus 6 times 0, 2 plus 4 times 0, minus 4 times 0 squared, which is 0. So we don't know, inconclusive. We don't know. And at the point root 3/8, negative half, sorry. Negative a half. Oh man. So minus 6 times minus a half, 2 plus 4 times minus a half, minus 4 times root 3/8 squared. Oh, that's 0 just there, isn't it? 2 minus 2. So that's negative, and so therefore it's a saddle point. And the other one's going to come out to be a saddle point as well. So we don't get any maximums and minimums. They're all saddle points, or we have no idea what the hell is going on at this point here. But for completeness' sake. A saddle point again, because that's definitely a negative number. We've squared something which makes it positive and then put a minus. So unfortunately, my example didn't produce a maximum. Sorry. So what would have happened is that it would have come out to be positive, and then I would have had to go back here and sub it into just one of those two bits and decide whether that's positive or negative. So if this had come out to be positive, then I would have gone back here and gone, oh, that's negative, and so that would be a maximum. How are we feeling? Took longer than I thought, but that's okay. I'm glad I did it justice. How are you feeling? So you've only got 2 hours. I can imagine them cutting some of that work for you and saying, here's what the discriminant is, and here are the critical points, classify them. But I also will say that finding critical points does require you to do partial derivatives, which is one of the things you're supposed to be able to do. So, yeah. All right. So last thing I wanted to say before I did any of that was I just wanted to make a quick mention of tangent planes. Tangent planes, there's a different way of making a tangent plane depending on how you've created your surface. So you can imagine a tangent plane as something that has the same slope as your function does in the x and y directions. And so you can say, so you could have z equals f of x, y. That's what we're imagining. And then what you could say is, well, your tangent plane at the point AB, where z is, well, above the point AB, if you like, or below it, has the same slope as your function does in both the x and the y directions. And so you could say that it's equal to z equals the slope in the x direction times x plus the slope in the y direction times y plus a constant. So that's one way of making a tangent plane. So I'm just going to make a new function, which is the plane itself, and it has the same slope in the x and y directions, and so they will be the coefficients of x and y, because that's what slopes are. If I differentiated this with respect to x, I would get that number. And if I differentiate this with respect to y, I would get that number. So this function is a plane, and it has the same slope as my original one at the point I'm thinking of. So that's really cool. So that's one way. Or if your function is being thought of as a function of x, y, and z equal to a constant, then we have to think about the tangent plane in a whole other way. So this one is thinking that every point in space has its own calculation for what this function works out to be. And I've only chosen the ones where it's equal to the particular constant I'm thinking of. So it might be f of x, y, z equals 0, f of x, y, z equals 10, doesn't matter. And this function, when I'm on the surface, isn't changing, because it's always equal to c when I'm on the surface. And so the derivatives should all be 0. That's the plan. And so you can create your tangent plane in a different way. You can say your tangent plane at AB, damn it, can I call this K? ABC has is that. So you've got an x minus a and a y minus b and a z minus c. So if you imagine moving from the point ABC to the point XYZ, then this is how far you've moved in the x direction, and this is how far you've moved in the y direction, and this is how far you've moved in the z direction. And then if you multiply that by the rate of change in the x direction, and the rate of change in the y direction, and the rate of change in the z direction, this total amount here must be how much this function has changed when I've moved in this direction. But if I'm on a tangent plane, so if I'm on the surface of the function, I'm very close to it, the function value won't change, and so the answer will be 0. That's why it's the way it is. So these are two different ways of making a tangent plane, and you can choose which one you've got based on the situation you're in. So just as an example, this surface, it's a ball, by the way. It's like an ellipsy sort of shape, like a football. It's wider in the z direction than it is in the y direction, and it's wider in the, it's narrower in the y direction than it is in the z, and it's even narrower in the x direction, just in case you're wondering. This surface is one of these. We have a calculation involving x and y and z, and it produces a specific answer. Just a second, I'm just going to figure this out. Find the tangent plane at the point half. Zero, half. Okay. Let's just check if this point really is on the surface. 3 times a half squared would be 3 times a quarter, so that's 3/4. 2 times 0 squared would be 0. And a half squared would be 1/4, and 3/4 plus 1/4 is indeed 1. So this point really is on the surface. Okay. And 3/4 plus 1/4 really is 1. Okay, so it really is on the surface. If your lecturers have made the mistake of giving you a point that isn't on the surface, you would say, this point is on the surface. It doesn't have a tangent plane. Okay, fun. That happened in the exam, but they'd probably cut that question if it was impossible. And they do have people checking these things. But sometimes it's not impossible. Okay. And so the next thing I want to do is I'm going to say that the tangent plane of this one can't be made in this way because I don't have a z equals. I'm going to need to make it in this way. And so what I'm going to do is I'm going to let f of x, y, z be this thing. Like that. And I'm going to imagine that if I move away from the point 1/2, 0, 1/2 a little bit, then the function value won't change. So all the derivatives should be, so when I combine the derivatives with how far I've gone, it should produce 0. So I'm going to go f on dx. So f sub x is 3 times 2x, which is 6x. And oh, this is that there aren't any other x's there. And f sub y is 2 times 2y, which is 4y. And f sub z is 2z. Right, so this was a nice one because I didn't have any of the x's times by the y's or the z's, and so that was fine. And so at this point, no, I can fit it in here. No, I'm just going to do it again. At this point, f of x is 6 times 1/2, which is 3, and fy is 4 times 0, which is 0, and fz is 2 times 1/2, which is 1. And so therefore the tangent plane is has this equation. Three times x minus the place where it started, plus the y slope times y minus the place where it started, plus the z slope, which was 1 times z minus the place where it started, equals 0. You can leave it like that if you want. It's a perfectly good plane equation. But you can also expand it out, like 3x minus 3 over 2 plus z minus 1/2 equals 0. So we've got 3x plus z equals 1.5 plus another half is 2, which turned out to be very neat. Doesn't always work out that way. But separately, just as a separate example, my surface is the graph of xy cubed. Just making up something. Do I really want that one? Nope, I changed my mind. x times e to the power of xy. Yeah, let's do it. Then find the tangent plane where x is equal to 1 and y is equal to 0. And so I know that f sub x, so I'm going to have to use the product rule because they've both got an x in it. Keep the x and differentiate the e to the xy. And the derivative of e to the x would be e to the x, but I have to multiply by the derivative of that, which is y. Differentiate the x with a 1 and keep the other bit. And f sub y, that x counts as a constant, so it will still be there multiplied on. The derivative of e to the x is the same, and then I'll multiply by the derivative of that, which is x. And so, at this point, fx at the point 1, 0 is e to the 1 times 0, 1 times 0 plus 1, and e to the 0 is 1 times 1 is 1, and fy of 1, 0 is 1 squared e to the 1 times 0, which is also 1. Damn it, I really should have made it different to that, but that's what we've got. And so therefore, the plane has equation z equals 1x plus 1y plus c for some c. But I don't know what the c is. And so I'll get, I need to sub in this point to figure and also sub it into this so that it has the correct z value at this spot. So I know that f of 1, 0 is 1 times e to the 1 times 0, which is 1. Everything's 1. Sorry, should have put another number in there. And so this is supposed to produce the same answer when x and y are these points. So z coordinate should be 1 at the point 1, 0. Because that's what the function does. And so I'll go so the z coordinate should be 1 when x is 1 and y is 0. And so I get c has to be 0. And so therefore the equation is z equals x plus y plus 0. How are you feeling? There are alternative ways of doing it. We could have done this one by the same way as the other one if we wanted. We could have said, or the graph of f of x, y is x e to the xy is the surface with equation z equals x e to the xy, which is the same as x e to the xy minus z equals 0. And I can call this my function and do what I did in the other one. And so I could have done the 3 partial derivatives, g sub x, which would have come out to the same answer as this one. And g sub y, which would have come out to this answer. and g sub z, which is -1. And so at this point, I would still need to figure out what the correct value of z is for the point that I'm interested in. So I still need to do that part. Z coordinate is f of 0, 1, which worked out to be 1. Sorry, 1, 0, sorry. And so at the point x is 1, y is 0, z is 1. G sub x works out to be whatever it works out to be. It came out to be 1. G sub y worked out to be 1. And z, g sub z, well, it's always -1. And so the plane equation is this number times x minus the matching point plus, sorry, this came out to be 0, didn't it? This number times x minus y minus the matching point plus this number times z minus the matching point equals 0. And when you rearrange that, no, it is 1. It was 1, wasn't it? They're all 1. Sorry, getting myself mixed up. And so I get x minus 1 plus y minus z plus 1 equals 0. X plus y equals z. Because the 1 minus 1 cancel. So that's the alternative way of producing the same answer. You get to choose. You are allowed to technically skip some of the working in the middle if you want. But, I skipped these bits of the working here, but that's because I already did them earlier. Yeah, you can't choose if it's not written as z equals already. You can rearrange it to be that way if you want, though. So, yeah. All right. I'm just going to make sure I don't lose my order of my pages. I don't know how you feel, but I'm proud of what I did there. That was good. Since they introduced the new bit of the curriculum that had the second way of making a graph, making a surface in 3D, I haven't done something that addresses the fact that there's two ways. So I'm really glad that I've done it. Okay, so in that case, we've done that, and that took us way longer than I expected. And so I will talk about series stuff, because that was the most votes that we had. I had 3 people say that, so I'll talk about that. So I talk about series most years. There's lots of revision seminars on series, but it's really important to do it for every cohort of students, because you watch enough videos in your life. It's sometimes nice to see it live. So, yeah. Don't forget, one of the advantages of being here in person or live on Zoom is that you can ask me questions. Please do. Okay. I might start at the reverse end and start at Taylor series and go back to the other series afterwards. Okay. No, maybe not. Maybe I'll just talk about. Give me a second. Yeah, all right. I'll just talk about them generally. Point of a series is that it's basically a thing you can write down using the symbols we've created for other stuff. And so we've created some notation. and we can add stuff together. Yep, I will, definitely, Taylor. We've created some notation. We can add stuff together, so we can create a notation with sums in it. So we can have a formula like nah, not that. Just making up crap. I could have just put that there, but I really wanted something else. Sure, that'll do. Just a random thing. And so we're used to, well, we're not, but back in Maths 1A, we did upper and lower sums, and we were able to have things like, you know, something like this. And there'd be an I here and an N here. And what we're going to do is we're going to make things that add up infinitely many things. And so we can go, just as a short version, this would be when n is 1, I get 1 plus 2 over 1 factorial. And when n is 2, I get 2 plus 2 over 2 factorial. And when n is 3, I get 3 plus 2 over 3 factorial, and so on, forever. And so this would be 3 plus 4 on 2 plus 5 on 6 plus, what's the next one? 4 plus 2 over 4 factorial. 6 on 24 plus, and so on. So there's nothing stopping me writing this, right? Whether it makes sense to do a sum for infinitely many terms is irrelevant at the moment. Like, there's nothing stopping me writing this collection of symbols. And that collection of symbols is a series. An infinite series, technically, because it goes on infinitely many steps, but that's what it is. And so I can write this sort of ridiculousness, and I have to decide what that means. And what it means is I need to do a running total. And so I'll have the running total 3, and then 5, and then 5 and 5/6, and then 5 and some number of 24ths, and so on. I have this running total, and if that running total approaches a particular number, I declare that that is the answer for this series. Five and 5/6, and 3 plus 5/6 plus 6, 3 plus 4 on 2 plus 5/6 plus 6 on 24. And so on. And I can do this sequence of running totals. I call them running totals. The official name is partial sums. But running total is what I call it. So if you're running total, that sequence of numbers gets closer and closer to something, then I declare that that is a number. I declare that this is what the sum is equal to. Now, I don't know what that limit's going to be. I just have no idea, just what ifs. But that's how you do it. That's the definition of what the sum adds to. That's fine. So the question is there going to be a limit? And that's called converging. You say the series, oh, damn it, converges. And if the limit doesn't exist, we say it diverges. If not, we say it diverges. Okay. Cool. So some series converge, some series diverge. It's not to say that, so it's almost as if we're allowed to have this thing as an object that exists, whether it converges or diverges. It's just that that's what it is. This list of symbols is representing an actual number, or sometimes it isn't representing an actual number. Sometimes it doesn't have a limit because it flips and flops back and forth between two different numbers. Sometimes it doesn't have a limit because it goes to infinity. We don't distinguish between those, not in this course. Some mathematicians do, and they have lots of fun, like doing things like proving when you add up all the natural numbers, you get minus a 12th or something ridiculous like that. Don't believe them, it's not the truth. So the problem is that when you look at a series, can you tell if it's going to converge or not just by looking at it? And the answer is no, not really. But there are a few calculations you can do that can help you decide. And they are called the convergence tests. Now, I've done many a seminar on the convergence tests, but there are 3 convergence tests. And a bit. There's a recognize that it's one of the series that people are familiar with already. Okay, but before I do on the convergence tests, I want to say another thing, which is we can do this even worse. We can also have a formula that's not just this, but also has an x in it, which is unknown. Because technically these n's aren't unknowns because they're going to be subbed in for all the numbers from 1 to infinity. I know what n is, it's all of these numbers. But you can put an x in there like that. And so what this is that different values of x will produce different series. When x is 0, I just get the series that's a sum of infinitely many zeros. When x is 1, I get the sum, which is the series which is the same as the one I had before. When x is 2, then I get whatever I get. And so this is called a power series. And it's basically different series for different x's. And so I can ask myself, which x's make it converge and which x's make it diverge? Which x's make it converge? That's the question I'm going to do. So subbing in a different x gives you a different series. Does that one converge? If I sub in x equals a half, does that one converge? If I sub in x equals 10, does that one converge? I want to know the collection of all the x's that make it converge. That's what I want to know. So that's the difference between an ordinary series and a power series. A power series has an x in it that makes it a variable that means that it's different series for every x. And it's called a power series because of this thing here. So you could imagine putting like 2x there instead. That wouldn't be a power series. It would still be the same idea that different x's produce different series, but power series is all we're interested in this course. Okay. Right. So the decisions that you make for individual series to see whether they converge or not, you have to make them all at once for different x's when you do power series. And there's only one test of convergence that applies to all of them different x's simultaneously, and it's the ratio test. And that's why we learn the ratio test, so that we can use it on power series. So there are these tests. The test for convergence in Maths 1B, there are 4. 4? Anyway, I call the first one 0, so I always have trouble. So test 0 isn't a test, it's just recognize it and know the answer. Test 1 won't tell you whether it converges, but it will tell you whether it diverges. In your notes, it's called the necessary condition for convergence. I call it the divergence test. So if you search for it online, divergence test will get you the thing, like if you Google it. So I should probably put this. This is what it's called in your notes. This is what I call it. Number 2 is the alternating series tests. And number 3 is the ratio test. They are the tests for convergence that are in Maths 1B. If you ever do another course about power series, such as Real Analysis 2, you will learn even more convergence tests. Won't that be fun? If you choose not to do Real Analysis 2, then you will live in blissful ignorance. So they are fun. I quite like convergence tests. Okay. So I've talked about this many times. The recognize it test is basically the harmonic series and recognizing a Taylor series. So you are allowed to, if you see something and you go, you can just say it's the harmonic series. It diverges. If they don't ask you to prove it, then you can just say, there it is. I recognize the harmonic series. And there's another one. That's a geometric series. Different values of x will make it converge or diverge. You may notice that what you have is a number to the power of n. And this is a geometric series. So it's technically a power series. And the decision about which x's make it converge and which x's don't is that it diverges when the absolute value of x is greater than or equal to 1, and it converges when the absolute value of x is less than 1. And then what's the other ones? Oh, there's 2 more. This is a P series, they call it. So it's not a power series because the unknown is in a different spot to what it is for this, but it diverges when P is less than 1 or equal to 1. When it converges and P is greater than 1. So 1 over n squared, converge. 1 over n cubed, converge. 1 over n to the power of 1.5, converge. 1 over root n, that's n to the half, diverge. And then the last one is this one. That's e to the x. That's what it is. And it always converges, no matter what x is. Yay. I should point out with the geometric series that when it does converge, what it converges to is 1 over 1 minus x. So these are the only two that you are absolutely certain what the answer is going to be. All the other ones will say it converges. Don't know what the answer is, but there is one. Yeah. Cool. So if you have a series which is n equals 1 to infinity or 0 to infinity, doesn't matter where it starts. If the limit as n goes to infinity of an is not 0, then it diverges. If the limit as n goes to infinity of an is 0, then we have no idea. It could converge, it could diverge, no idea. This is not enough information to tell you it definitely converges, but this is enough information to tell you it definitely does not converge. So this an is standing in for the thing in this spot here. I would much prefer if it was like f of n because it looks like a function, but that's just not the way we do it. The alternating series test is if you've got a series like that, and it has 3 pieces, you need it to be an alternating series. So the ANs actually have to be -1 to the n times something, where this is positive. This is how I write it anyway. So if you see a -1 to the power of n in there, that makes it an alternating series. And this one only applies to things like that. And number 2, the limit as n goes to infinity of the Bn has to be 0. I mean, it can't be not 0 or it wouldn't converge. And number 3, at some point, Bn is more than Bn plus 1 and it's more than Bn plus 2 forever. So strictly decreasing. If all 3 of those things happen, then it converges. Most people don't care too much if you don't explicitly prove that it's decreasing. You can usually look at it and go, well, obviously. Like it'll be like 1 over n, and you go, well, as n gets bigger, that gets smaller, yay. But all 3 of those things have to be true, and it'll converge. If one of them isn't true, then you can't use the test and it doesn't work. Like it tells you nothing. Well, I mean, if this isn't true, then it definitely diverges. That's this one. So, would you like an example of the alternating series test? Yay. I will not start at 6. I will start at 7. That will avoid it being 0 on the denominator. I'll do 2 examples. So I can use the alternating series test because of the 1 minus 1 to the n. If that wasn't there, it wouldn't be an alternating series test. So I can see a -1 to the n, and it doesn't matter if it's -1 to the n. It could be an n plus 1, it could be an n plus 2, doesn't matter. So I'm just going to put that in just for the sake of it. Doesn't matter whether it's n plus 1 or n plus 2 or n, as long as it's not like 2n, because -1 to an even power is 1, and so it doesn't really count as an alternating series. So this is the Bn that's in my version of the theorem. Don't call it Bn in your exam because the lecturer won't know what that means. Okay, so we're going to say that to the limit as n goes to infinity of 2n plus 5 over n minus 6. I'm going to have to figure out what that limit is. Well, I know how to do limits as things go to infinity. There was a whole thing in this course about it. I'm going to divide the top and bottom by the biggest power of n that I see in the whole fraction. And so that's going to be 2 plus 5 over n, 1 minus 6 over n, which is, when n goes to infinity, that and that are both 0, which is 2. And the limit of this thing, if it's not 0, then it doesn't converge. So it diverges. Yay. I didn't have to use, actually, I didn't even need the fact that it was an alternating series at all. But the alternating series allows you to ignore this bit. Let's do this one. Slightly different. Instead of having an n minus 6 on the bottom, we've got an n minus 6 squared. So it is an alternating series. 1, it's alternating. 2, I need to do the limit of this thing. So I'm going to divide by the biggest power of n that I see, which is n squared, because if I did expand this out, it would be an n squared. Technically, I can divide by n minus 6 squared. So that's what I'm going to do. No, I'm not. I'm just going to divide by n squared. So when I bring, they've both got a squared, so I can bring that squared out. And that means I'll be doing n minus 6 divided by n, which is 1 minus 6 on n. And so when n goes to infinity, I get 0 plus 0 over 1 minus 0 squared, which is 0 divided by 1, which is 0. So good, that's supposed to be 0. If it wasn't 0, it wouldn't converge. And then I need to be sure that it's strictly decreasing. So as n gets bigger, does the answer get smaller? And, oh man, yes, I suppose. So, yeah, I reckon it's okay to just say it. Pretty sure it's okay. If I was in the mood, I'd differentiate it, right? And then show the derivative was negative, and that would show that it definitely decreases. What's that? L'Hopital's rule? Oh, no, I'm not trying to do limits anymore. I'm trying to show it's decreasing. L'Hopital's rule would have worked here as well. You can probably just get a machine to graph it. wanted to differentiate it. But that's what I'd have to do. I'd have to decide it was decreasing and be sure. Ah, I've got a plan. If that was an n minus, oh, I've got it. If it was an n minus 6 on the top, I'd be good. So I'm going to put a minus 6 and a plus 6 in here. And so I'm going to have two lots of n minus 6 plus 12 plus 5. Yeah. So that n minus, if I go this divided by that, I get 2 on n minus 6. If I go this divided by that, I'm going to get 17 on n minus 6 squared. And that is definitely decreasing. Both of those are decreasing, and so therefore the total is decreasing. Okay, cool. Yay, and this would have done my limit actually really well, because as n goes to infinity, these both go to 0. I should have done that to begin with. That would have been cool. Yeah, okay. Oh well. And that's the ratio, that's the alternating series test. It might not look like an alternating series to begin with, but just be careful that it might actually be one. I just wanted to point out that this is going to be bad. I have no idea this is going to be bad. But what I do notice that if I pull a minus sign out, and this number is always positive if n is more than 1. So it really is an alternating series after all. I don't like my chances of doing this though, because n to the power of n is like, oh, why? I think this won't converge because n to the power of n is bigger than n factorial is. So, because n to the power of n is like n times n minus 1 times n minus 2, no, n times power is just n, and n factorial is n minus 1, n minus 2, n minus 3. So it's n factorial is smaller, so the top is bigger than the bottom. And so it's not going to converge. But I just wanted to point out that it's a thing. Look, it's alternating. So just wanted to point it out. I choose not to do the alternating series test. I just wanted to show that it really was an alternating series. Okay. So ratio test is the last one. And the ratio test goes like this. If you have this, then what you do is you do each term divided by the one before it. Is that right? Or the other way around? Yeah, no. And then you do the absolute value of that. And then you do the limit as n goes to infinity. And three things can happen. It's either less than 1, in which case it will converge, or it's more than 1, in which case it will definitely diverge, or it's 0, in which case we have no idea. Could be anything. That's the ratio test. Now I have other things on the ratio test, but it's very useful for power series. Because if you've got a power series, then there's an x to the power of n. Like that. And so this entire thing is the an that we're talking about. And so the an plus 1 and so when I divide them, this divided by this, I end up with this divided by this is just x. Because you subtract the exponents. And this divided by this is a fraction thing. So this divided by this is here. The fractions will end up the way they were. And this divided by this is x. And what you normally do is you rearrange it so that the things that are similar are next to each other. And so you've got n factorial, n plus 1 factorial, n plus 3 over n plus 2, and x. And so your absolute value of an plus 1 over an, in fact, these are all positive numbers anyway. Oh, crap. And so we want to do the limit of this as n goes to infinity. It's going to be 0. Yay. I just had to do one more thing. N plus 1 factorial, we have to multiply everything to get to n and then multiply n plus 1. And so this is already made of n factorial times another n plus 1. And so I actually, when you cancel those two, you get 1 over n plus 1. And so I'm going to get the limit of this is 0, the limit of this is 1, and the limit of this is the absolute value of x, and so I'll get 0. And that number is indeed less than 1, and so therefore it converges no matter what x is. Sometimes you get it only converges when the absolute value of x is less than 1, something like that, which is what happens with the geometric series. And essentially what we're doing is we're comparing it to a geometric series. That's what we're doing. You know, what if you'd gotten something like this, like that? Then you would say, not like that. What if you'd gotten that at the end? Then you'd say it has to be less than 1 to converge, and so the x would have to be less than a half. And so we'd say converges for x between minus a half and plus a half, because that's what that means. If your x wasn't an x, but it was just a number, then you'd just get an answer. You wouldn't say, well, it converges for any x. You'd just say, well, this is my answer, and it converges or it doesn't converge. All right. I'm happy to keep talking for a bit. Feel free to leave. Feel free to stay. I will not be offended either way. But I did want to talk about Taylor series. We promised to talk about Taylor series, so I'm going to. So I sort of did both series and power series together. I hope that was okay. What I will say is just it's really important to check if you recognize it before going to all the effort of doing the ratio test. Because if it's a harmonic series, you'll go, oh, look, it's a harmonic series. And just also with the harmonic series, you could just as easily have an n+2 here on the bottom. It wouldn't matter. Any linear thing in n counts as a harmonic series, and it definitely diverges. So it's something that happened in one of the assignments, but they didn't technically put it in the lectures. So I expected people to just make that decision, say, you didn't tell them that. So just telling you now. Okay. Taylor series. Are a special kind of power series. And what they are is an attempt to write your function as a power series. So you have a function, traditionally f of x, and you want to rewrite as a power series. So you'll have f of x is going to be the sum from n equals 0 to infinity of a n x power of n. You can call it a if you want. Technically, this entire thing is an, but we're a bit sloppy with that in maths. And so that's the same as a0 plus a1 times x to the 1 plus a2x squared plus a3x cubed plus forever. That's what a Taylor series is. Technically, this is the Maclaurin series because it's just got x's. Or we could write it like this. Something like that, x minus c to the n. I think sometimes they'd call it a. Doesn't really matter. And so this would be a0 plus a1 x minus c plus a2 x minus c squared plus forever. And this is a Taylor series center C with center C. Or sometimes they call it a Taylor series about C or around C or at C. Any of those are things that they can say. So it's basically Taylor series with some statement that seems to be saying that C is a location. Any one of those is fine. Okay, and it's technically a Taylor series for the function f of x with center C. So it's because it belongs to the function that you have. Because different functions will have different numbers in these spots. All right, cool. So the first thing to know is that if a function has a Taylor series, not all functions can be written this way. That's just pointing it out now. Doesn't work for every function. But for all the functions we care about, it does work. So not all functions can be written this way. Not all functions can be written this way for every possible C. So sometimes there are functions that you can't write using C equals 0, for example, mainly because they don't exist when C is 0. But if they can be written this way, then there's only one way. There's only one way. Okay. Cool. So we're going to declare right now, without doing any proofs, two classic Taylor series. Here we go. If this is my function, then its Taylor series is this. Oh crap, I think I wrote something wrong on my previous pages. Back here when I do the geometric series, it has to start at 0 in order to come out to this sum. It doesn't have to start at 0 in order to tell whether it diverges or not, but it has to start at 0 if it wants to be this sum. So that's the secret there. Geometric series is a Taylor series. It's a Taylor series with center 0. And the other classic known Taylor series is e to the x. That. So the long version of this is 1 plus x squared plus x cubed plus forever. And the long version of this is 1. So x to the 0 is 1. 0 factorial is 1. X to the 1 divided by 1 factorial is x. You'll get x squared on 2. You'll get x cubed on 6. You'll get x to the 4 on 24 plus forever. These are the two classic Taylor series that you're just supposed to know. Don't have to prove them, they just are. Not sure if they expect you to remember the Taylor series is for sine and cos. Sorry? So I'll do the one for sine. Sine is an odd function. Odd meaning that when you sub in a negative, you get when you sub in a negative number, you get the same answer as subbing in the positive number and then just minusing the answer. So meaning you can pull minuses out. So sine is an odd function, which means it only has odd powers. And so we put a 2n plus 1 instead of an n to make them odd. And then you also have to multiply by a -1 to the n. So that'll be x minus x cubed on 3 factorial plus x to the 5 on 5 factorial minus x to the 7 on 7 factorial plus and so on. And cos x is the same but with even powers. So that'll be 1 minus x squared on 2 factorial plus x to the 4 on 4 factorial minus x to the 6 on 6 factorial plus and so on forever. They are the classic Taylor series that people who ask you, who say, did you do Taylor series? And you answer yes, they expect you to just know these. So did you study Maths 1B? Oh, well, I expect you to know these Taylor series. I mention this now because if you do anything with differential equations, a course called Differential Equations, this will come up. If you do a course called Probability and Statistics, this will come up. They do it all the time in physics. Yeah. And look, when x is really small, x cubed is even smaller. And so when x is really small, sine x is approximately equal to x. That's how I know it starts with x. And when x is 0, cos x is 1. And so that's how I know it starts with a +1. Okay. That's fine. And if you have a Taylor series, it's only got 1. I mean, it might have a different one, e to the x minus 1. Like e to the x would have a different Taylor series if you wanted x minus 1s instead of x's. There would be different coefficients, but these are the classic known Taylor series with center 0. So if it has a Taylor series with center 0, then it's only got 1. If it has a Taylor series with center 1, it's only got one of those. So here's the thing. If f of x is indeed equal to a0 plus a1 x minus c plus a2 x minus c squared plus forever, then a0 will be f of c. And a1 will be f dashed of c. And a2 will be f double dashed of c divided by 2. And a3 will be f triple dashed of c divided by 3 factorial. And so what we end up with is this formula, which says that an will be f nth derivative sub n c divided by n factorial. So the coefficient of x to the n is this when you do a Taylor series. Yep. So if you want to find the beginning of a Taylor series for a function, then you are going to need to calculate derivatives and sub things in. Oh no, let's do this. So I'm going to do the Taylor series at x equals minus 1. Or at least the first 4 terms. So if the center is minus 1, I'm going to be having terms like this. X minus minus 1, which will be plus 1, and x minus minus 1, and x minus minus 1 cubed. That's what it's going to look like. Technically, it's going to go forever. That's what I want. And so my a0 is going to be found from the function value. And my a1 is going to be found from the first derivative. And my a2 is going to be found from the second derivative. My a3 is going to be found from the third derivative. So I have f of x is x e to the x plus 1. And so f dashed of x is product rule, keep the x, differentiate the e to the x plus 1. It'll be the same times by the derivative of that, which is 1, so that's fine. And then differentiate the x, which is a 1, and keep the e to the x plus 1. And so that's x plus 1, e to the x plus 1. And the second derivative would be keep the x plus 1, differentiate the e to the x plus 1, and then differentiate the x plus 1, and keep the e to the x plus 1. And so I've got now x plus 2 e to the x plus 1. Oh, wow, look at that. I've got a guess now. The third derivative looks like it's going to be e to the x, it's going to be an x plus 3. Yay. So this is as far as I need to go to get 4 terms. 1, 2, 3, 4. So f of minus 1 is minus 1 e to the minus 1 plus 1, which is minus 1. And f dashed of minus 1 is minus 1 plus 1 e to the minus 1 plus 1, which is 0. And f double dashed of minus 1 is -1 plus 2 e to the -1 plus 1, and e to the that's 1, so I'll get 1, and f triple dash of -1 is -1 plus 3 e to the -1 plus 1, which is 2. And so my coefficients are going to be, A0 is going to be f of -1. If I hadn't put my page sideways, I would have done another column of the table, but I ran out of space. So A0 is f of -1, which is -1. A1 is f dashed of -1 divided by 1 factorial, which is 0 divided by 1, which is 0. A2 is f double dash of -1 divided by 2 factorial, which is 1 divided by 2, so that's a half. And A3 is f triple dashed of -1 divided by 3 factorial, which was 2 divided by 6, which is a third. And so therefore, I ran out of space. I never managed to finish these in one page. Therefore, my beginning of my Taylor series is -1 plus 0 lots of, I'm just going to put it in explicitly, plus 1 plus a half lots of x plus 1 squared plus a third lots of x plus 1 cubed. And I have the first 4, they often say the first 4 non-zero terms. This is the first 4 literal terms. If I want the non-zero terms, I'd have to go to the next one. Annoying. That's finding a Taylor series. Yep, that's it. Not anything fancy. I can make a guess at what the actual terms are for every position, because it looks like this pattern is going to continue. So just as an aside, it looks like the nth derivative is going to be x plus n e to the x plus 1. And so therefore the nth derivative with -1 subbed in is going to be -1 plus n e to the -1 plus 1, which is n minus 1. And so therefore an is going to be n minus 1 on n factorial. And so my Taylor series is actually going to be n equals 0 to infinity that. Yay. So I actually have, and it's okay to just make a guess at what the right formula is. Do you not put in? So I put in the summation notation when there's a formula, but I can't really put in the summation notation here because I didn't know the pattern that these coefficients followed. Does that answer your question, Talia? Yeah. So if they specifically ask for what are the first 4 terms, then don't put it in some notation. Just literally write it out like this. If they ask you what is the Taylor series, then it has to be infinitely long, and so you're going to have to do this with an infinite sum. Is that better? Cool. Now I made a big guess here. That was a big guess. I just wanted to point something out. If something has a Taylor series, it's only got 1. And so I could have possibly, if I was very lucky, figured out what this was from the Taylor series for e to the x. But I think this is fine. Yeah. Okay. Cool. 5 more minutes. Anyone have any questions they want me to talk about with Taylor series? before I talk about any? Yep, because otherwise I'll just stop. I'm okay to continue for another few more minutes. Doing the chat, sometimes it takes a while to type it, so we need to make sure we give people time. Okay, so in a technical sense, you're supposed to check if this converges. I mean, this is the Taylor series, but we can't really write the equals here unless it converges. So technically, not allowed to write the equals unless I'm sure that this converges, but it does. So that's where you would do the ratio test to see if it really does converge. But it has to, because if there's an e to the x in it, and that converges, and the one for x does as well, so it's fine. Yep. Cool. I am going to stop the recording.